Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 6 on tangents, secants, and their angles. Now we've already talked about tangents, we've talked about chords, but secants will be a new thing for us. So let's begin by discussing what a secant is. So secants to a circle. We've now seen chords and tangents of circles, and in this lesson we will learn about secants. Let me bring that right up to the top so that we can talk about what a secant is. Here we go. A secant is a line that intersects a circle exactly twice. It can be thought of as an extension of a chord. In the diagram shown, AB is a secant intersecting at D and E, while BC is a tangent intersecting only at point F. All right, so secants are an easy enough thing to understand, right? They're a line or even a segment that intersects a circle twice, but so does a chord, right? So here we've got like chord DE, right, endpoints on the circle, but then we have secant AB cutting across the circle twice, as opposed to tangent BC, which just nicks the circle right there, right? Just touches the circle at that one point. Now, there are various theorems that relate the angles secants and tangents make to the arcs that they intercept, all right? And we'll get into those theorems in just a bit. Before we learn them, though, we should practice the skill of identifying the intercepted arcs, which can actually be a little bit challenging. All right, this is where a highlighter actually can come in very, very handy if you have one, all right? Especially if you have multiple highlighters of different colors. Let's take a look at exercise number 1. Given the diagram below with secants AB and AC and tangent DE, answer the following question. Letter A, what two arcs are intercepted by segment AB and AC when they form angle A? All right, so here's what I'm getting at, right? We've got angle A up here, which is formed by the secant AC and the secant AB. Let me just draw those in, or at least cover them up with my blue pen. Okay, now the key here is that that angle, when it's created by those two secants, intercepts two arcs on the circle. What are those two arcs? Well, here I'm going to go to a highlighter really quickly. Okay, and one thing I can see is that they intercept the circle there and they intercept the circle there, right? So what I can see is that the two arcs that are intercepted are arc FG and arc HK, or GF and KH. Of course, that doesn't matter, as we've discussed repeatedly. So let's write those down, right? So we've got arc FG, or GF, and arc HK. All right. Now, the reason this is going to become essential is that the measure of angle A is going to depend on the measure of those two arcs that are intercepted. In fact, every one of these theorems in terms of how tangents and secants interact to create angles are going to depend on the arcs that are intercepted. Let's take a look at letter B. What arc is intercepted by secant AC and tangent DE when they form angle AKD? All right, so again, what I'm going to do is I'm going to erase all of this, and let's take a look first at angle AKD, right? This angle specifically. All right. Now, notice here, it's just what arc, not what arcs, okay? And this one's actually pretty easy to see. So the arc here is going to be the arc that goes from point F down to point K. That arc is intercepted by that angle, okay? So we can say arc KF or FK, either way. So let's go with arc KF. Okay, simple enough. Now, of course, you know, this line and this tangent actually create two angles. They create angle AKD, but they also create angle AKE. So let's take a look at letter C. What arc do those same segments intercept when they form angle AKE? Why don't you go ahead and pause the video now and see if you can figure out what arc is intercepted by that particular angle. Well, there's a lot of different ways of naming this arc, but first let's draw the angle. We've got angle AKE. This ends up being a major arc. It goes from that intersection point all the way down to there. Okay. And we've got to name this major arc with 3 letters. Now, it should begin and end with F and K, and we can either use point G or point H in between. It doesn't really matter which. So you could say something like F, G, K. That would work. You could say K, H, G. That would work. There's a number of different ways of saying it, all right? The most important thing isn't really how you write this. Let's see, did I make a mistake here? KHF, absolutely, KHF. If I say KHG, I've stopped a little bit too early. And again, it doesn't matter particularly how we name it, assuming we name it correctly. What will be important is being able to identify the arc so that we can figure out how large the arc is, and that will then help us figure out how large the angle is. All right, and that is a little bit challenging, as apparently I just showed. Now, all theorems involving the angles and arcs will be presented in this lesson without proof, which is weird for us. Very often we either prove a theorem and then we use it, or we state a theorem, use it, and then we prove it. Those proofs will be done in a later lesson, in theory in the next lesson in this series. Now, the first theorem involves the angles created by chords and tangents. So let's take a look at that one, and it's probably going to seem awfully familiar to it. We'll call it the tangent chord angle theorem. The measure of an angle formed by a chord and a tangent will be equal to 1/2 the measure of the intercepted arc. Now that sounds a lot like the inscribed angle theorem, and it really has the same form as it, right? The inscribed angle measure will always be 1/2 the arc that it intercepts, and the same is true when you have a tangent and a chord that form an angle. So let's apply that in exercise number 2. In circle O, tangent CD intersects chord AB at point A such that the measure of arc AEB is equal to 266 degrees. Great, awesome, right? Make sure again that you understand that, right? The measure of arc AEB is 266 degrees. That's EB, right? That is 266 degrees. Makes sense, right? It's quite a large arc, right? It doesn't go all the way around the circle, but it's getting there, right? Well over 180 degrees, more than half. Now, letter A asks us to do something very easy, which is to find the measure of arc AB. Why don't you go ahead and pause the video and do that? Well, since I did such a beautiful job highlighting that, let me do one more highlighter, because, you know, again, why not? Right, there's our arc AB. And of course, arc AB is the minor arc to arc AEB's major arc. So in order to find, I better go back to pen, otherwise this is going to look really funny, right? In order to find the measure of arc AB, and I went with green, which is the one color you never want to go with. If I want to find the measure of arc AB, I'm just going to do 360 degrees minus 266 degrees, right? We've got our nice simple calculator. We don't need anything fancy for just simple subtraction and all of that. And we find the measure of arc AB is 94 degrees. Might as well write that on my diagram. And then letter B says find the measure of angle BAC. Right, that's just a direct then application of this theorem. The measure of angle BAC is going to be 1/2 the measure of arc AB. So that's going to be 1/2 of 94 degrees, and that's going to be 47 degrees. Now, for a moment, before we move on to the next exercise, I want to give a nod to something that might be going through some of your heads. If this problem had given all this information and then asked for the measure of angle BAC, One way to have done it would have been to find the measure of angle DAB by finding half of the 266, which would have been 133 degrees, right? And that would have then ended up being this particular angle. And then we could have subtracted the 133 from 180 and gotten our angle of 47 degrees. So, you can obviously get these angles in a couple different ways. So let's keep going. All right, now let's talk about angles created by secants and tangents, because that's a little bit different. All the other theorems that involve tangents, secants, and their angles can be summarized in really a single statement. We will eventually see that these relationships all depend on the last one that we looked at, but that won't come until we prove them in the next lesson. So let's take a look at angles created by secants and tangents. The measure of an angle formed by two secants, two tangents, or a secant and a tangent intersecting outside of a circle can be found as 1/2 the difference between the measures of the two intercepted arcs. So in this case, right, when we've got two secants, a secant and a tangent, or two tangents, there are always two arcs that are intercepted. The deal, though, is that to find the measure of the angle that's exterior to the circle, we will simply subtract the measure of the smaller arc from the larger arc and then divide by 2 or multiply by 1/2, however you want to look at it. And I hope that everybody at the geometry level is comfortable with the fact that doing the subtraction and dividing by 2 or multiplying by 1/2 is exactly the same thing. Now again, just to kind of go through these very quickly, right? In this situation, when I have the measure of angle P, it's intercepting arcs CD and AB. So I'm going to do the measure of CD minus the measure of AB, and then I'm going to divide by 2 / multiply by 1/2. Here, where we have a tangent PA and a secant PC, that intersects arc AB and arc ADC. So I'll take the measure of arc ADC, subtract out the measure of arc AB, and again divide by 2. And finally, when we have two tangents, this is one of the more interesting cases, right? That's intercepting arc AB and arc ACB, a minor and a major arc that go together. So we take that major arc, ACB, we subtract off that minor arc, AB, and again we divide by 2. Really, all three of these theorems are the same theorem, right? When we have an angle that's created on the exterior of the circle by two tangents, two secants, or a secant and a tangent, we simply find the difference between the two intersected arcs and divide by 2. Not all that different than what we had when we had chords intersecting inside of a circle, but in that case we added the two arcs that were intercepted and divided by 2. Here we're going to subtract the two arcs intercepted and divide by 2. The rest of the problems that we're going to do in this set of problems, in this lesson, are direct applications of these theorems. And again, we'll prove these theorems in the next lesson. So I know you're excited about that, so I just want to keep telling you, don't be worried, it's going to happen. Let's take a look at exercise number 3. In circle K shown, it's known that the measure of arc AB is 28 degrees and the measure of arc CD is 84 degrees. What is the measure of angle P? All right, this is about the easiest case that you possibly get, right? Because we've got these two arcs that are intercepted, right? Arc AB and arc CD. Okay, the smaller one measures 28 degrees and the larger one measures 84 degrees. And our theorem simply says that the measure of angle P is going to be that larger one, 84, minus that smaller one, 28, all divided by 2. And again, this is very, very easy, right? You can even do it all at once if you so choose. 84 minus 28 divided by 2. Simple enough. At least it seems like it should be. And the measure of angle P is equal to 28 degrees. A direct application of that theorem, right? We've got our two arcs that are intercepted. We simply take the larger arc minus the smaller arc. We get a result, and we divide that result by 2. Very, very simple. Let's keep going. There's got to be things a little bit more challenging than this. Oh, how about one without a picture? Exercise number 4. Two secants intersect outside of a circle to form an angle that measures 38 degrees. The smaller of the two arcs intercepted measures 65 degrees. What is the measure of the larger intercepted arc? All right, well, here's what I'd like you to do. Pause the video right now, see if you can draw a good picture, if you even think you need a good picture, and see if you can find the measure of the larger arc. All right, so this one's a little bit more challenging, not only because we don't have a picture, but also because it's not a direct sort of plug and chug into the formula kind of thing, right? But first, let's take a look at what we have, right? We've got our circle, and we've got two secants, and we know that the angle formed by the two secants measures 38 degrees. We also know that the smaller of the two arcs that's intercepted is 65 degrees, and what we want is the measure of the larger arc. All right, we don't know what that is. We should probably give it a name, and by a name I don't mean arc AC or BD or anything like that, but maybe just give that a measurement of X degrees, just to kind of like really formally make sure we know that it's a degree measure. Now the theorem says, of course, that that exterior angle, that 38-degree angle, is going to be equal to the measure of the larger arc, X, minus the measure of the smaller arc, which is 65 degrees, all divided by 2. So in this case, we have to solve this particular problem by solving an equation as opposed to just plugging numbers into the formula and kind of cranking through what the formula tells us to do. But it's still relatively easy, and we've certainly played this game before when we were working with those chord problems. We'll just multiply both sides by 2, and we'll get 76 degrees is equal to X minus 65. And we'll just add 65 degrees to both sides. And we will get X is equal to, if my math is correct, 141 degrees. All right. Now you can always check to see if this is right by then doing the 141, subtracting the 65, dividing by 2, and ensuring that you've got that 38 degrees, right? Most of you will probably just trust your algebra, but it never hurts to check with the direct application of the theorem. All right, let's keep going. These are nice problems. They're pretty cut and dry. Exercise number 5. In the diagram of circle C shown, tangent AD is drawn and secant AB is also drawn such that it passes through C. If the measure of arc ED is equal to 58 degrees, then find the measure of angle A. All right, great. Well, again, let's just make sure that we understand what's going on here. With the theorem is going to say that we've got to have two arcs that are intercepted. Whoops, wow, that was weird. Somehow it decided to just make that into a straight line segment. Okay, that's better. So that's one of my arcs intercepted, and that's the other arc that's intercepted. All right, two arcs are intercepted, ED and BD. So what my theorem says is that the measure of angle A, again with the green, I just can't quite seem to hit that blue button. All right, so the measure of angle A is going to be the measure of arc BD minus the measure of arc DE divided by 2. Okay, now we know the measure of arc ED. It's 58 degrees. But in order to figure out the measure of angle A, which is what I'm being asked for here, I need to figure out what the measure of arc BD is. Pause the video now, see if you can figure out what the measure of arc BD is, and if you can, then use it inside of this formula to figure out what the measure of angle A is. All right, well the key here is, and it's a little bit subtle, right, is that secant AB includes a diameter, right? ECB is a diameter because it passes through the center of the circle. And that means that arc EB, right, this entire arc is equal to 180 degrees. So the measure of arc BD will be 180 degrees minus 58 degrees, which is going to be 122 degrees. Yep, I think that's right. So now we have the measure of arc BD, and that says BB. How about the measure of arc BD? So now the measure of angle A is going to be 122 degrees minus 58 degrees, all divided by 2. So let's figure out what that is. Let's clear out our calculator here. I think I'm going to do it all at once. 122 minus 58, all divided by 2, gives me 32 degrees. Okay. So a little bit more work there, right? We had to recognize the fact that we had a diameter in order to take one of the arcs that we were given and produce the other arc that we needed in order to solve this problem. Let's do one last one. All right, we've got to do the 2-tangent case. So exercise number 6. In the diagram of circle M, tangents have been drawn from point E through points A and B on the circle. The ratio of the measure of arc ACB to the measure of arc AB is 5:1. What is the measure of angle E? All right, so let's just again understand the basic premise of how to calculate angle E, right? To calculate angle E, we have to first have the measure of arc AB, but we also have to have the measure of arc ACB. Right? Those two are absolutely necessary in order to figure out the measure of angle E. In fact, let's just write it down, right? The measure of angle E will equal the measure of arc ACB minus the measure of arc AB, all divided by 2. And unlike the last problem, I don't have either one of these at this point, okay? Now, somehow, this piece of information has to allow me to find the measure of those two arcs. What I'd like you to do now is pause the video, see if you can figure out the measure of the two arcs, and if you can, substitute them into the formula and figure out the measure of angle E. All right, well, the real key here is that the measure of arc AB and the measure of arc ACB will add up to be 360 degrees because they are the minor and the major arcs that are formed by these two tangents. And in fact, right, that will always be the case. Whenever you have two tangents, the two arcs in question will always add up to 360 degrees. All right, in fact, maybe I'm going to just write that down. The measure of arc AB plus the measure of arc ACB is equal to 360 degrees. Now, if I had one of those two arcs, I could easily subtract it from 360 degrees, the way we did it in the last problem with the 180 degrees, and then I'd be off and running. Here, though, what they tell me is that that larger arc is 5 times the size of the smaller arc. So it probably makes sense, if you're thinking about this in terms of doing some equations, to call that arc x degrees and that arc 5x degrees, right? That would then mean that we can set up this equation, x plus 5x is equal to 360. That would mean 6x would be 360, and x would be 60. Okay? That then tells me that the measure of arc AB is 60 degrees, and the measure of arc ACB is 300 degrees. And once I have those two measures, I can now substitute it into this equation, and I'm going to find that the measure of angle E is 300 degrees minus 60 degrees, all divided by 2. That's going to be 240 degrees divided by 2, which is going to be 120 degrees. All right. So another nice problem. It gets a few different things involved, including the fact that the two arcs here will add up to 360 degrees, little ratio work there to figure out what the two arcs are, and then a direct application of the theorem. Let's wrap this up. So we saw sort of two distinctly different things in this lesson, right? The first thing that we saw were angles that were created by chords and tangents. And that really reverts back to our inscribed angle theorem. The angle created by a chord and a tangent is simply 1/2 the measure of the arc that it intercepts. Simple enough. It intercepts one arc, that angle, and its measure is 1/2 the measure of the arc. The other scenario is when we have an angle that's created on the exterior of a circle by two secants, two tangents, or a secant and a tangent. And in that case, we always calculate the measure of that angle in the same way. We identify the two arcs that are intercepted, we find their positive difference, and we divide by 2. Right? A very, very nice kind of theorem, easy to apply as long as you can determine the measure of the two arcs. All right? And sometimes that's more challenging than other times, as evidenced in that last problem. Now, in the next lesson, we will go ahead and we will prove those theorems. For now, though, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.